So welcome everyone to what should be an excellent panel on developments in North America with regard to CCUS, and we have a great set of speakers. Our first speaker is Ian MacGregor from Northwest Refining. Ian will, I think, be joining us live later, but we'll first hear from his voiceover. Then we'll be hearing from Abigail Gonzalez from Mexico. Talk about developments there, and we have Alissa Park and Howard Herzog from Columbia and MIT, respectively, or two of the kind of leading thinkers and speakers on CCUS. So we're kind of overflowing with excellent speakers. So maybe I'll leave it to Karis or Vic to queue up Ian's presentation. As a reminder, please do use. Don't use the chat, please use the Q&A.
Hi, I'm Ian from Northwest Capital. We practice merchant engineering. We find things that are broken, or we find places where something new is needed. We use our own money to build them or fix them, and if we do it well, we get to keep eating. I'm going to tell you about the story, our involvement with carbon capture and storage. This is Mr. Van Horn. He's the reason we have a railway in Canada. He had a great motto, and we've adopted it. A lot of what we'll talk about later in this slideshow sounds aspirational. That's the business we're in. Myself, my partner, we've made our livings for our whole life by being engineers. We are engineers in the sort of merchant engineer sense. We take on big projects. We use our own money to essentially make a bet on something, and then we try and make that bet valuable. We've worked everywhere in the energy business. Bottom left there is the Weyburn project in Saskatchewan, a large CO2 EOR project. Top left was the fourth largest gas plant in Canada when we owned it, and the bottom right was the world's largest offshore drilling rig during the time that we owned it. Those were all things that we kind of rescued from some kind of problem, took over and fixed them up, and that's what we like doing. We either like building new things or we like fixing things that are broken. When you look at the data on global warming and greenhouse gases, you start getting depressed quick. It's growing rapidly, and it's continuing to grow every year. Everybody's talking about it, and nobody's doing much. We got to get going. It's also kind of scary because we're continuing to make new uses. This graph shows what's happening with Bitcoin, and in 2021, it looks like Bitcoin will make more CO2 than the oil sands do. We've been making a lot of progress with electric cars. We sold about 3.5 million of them last year, and that's a lot, and it looks like great progress. But in the context of the car market, that's a really small amount. We have almost 1 billion cars in the fleet. We're adding about 50 million a year, so it's going to take a long time to get that car fleet converted over to electric, and the average car lasts about 12 years, so it kind of puts all of this in context. But I'm an optimist. When you send engineers a strong signal, they respond quickly and things can change really quickly. So this is a picture of a drilling rig I'm fixing up right now. It's a 1921 drilling rig, and I want to show you the evolution that's occurred in a bunch of areas in the energy business over the last 50 to 100 years. These are drilling rigs I built about 20 years ago. There's a huge amount of evolution in them during the period from the earlier picture to this one, and it just keeps happening. This is the last drilling rig we owned. It was the world's largest deep water, harsh environment, semi-submersible rig. We finished it up in Halifax and formed a new drilling contractor and drilled off the East Coast for about a couple of years, I guess. And that's me. I'm the guy with a white shirt on down on the left there. The same thing's been happening in refining. This is an old 1935 refinery that I'm moving from Montana up to my place in Alberta, and we're going to kind of restore it, get it working, so you can see how refining used to be done. The boiler's on the right side in that house with a stack on it there, and the still columns are in the middle, and the tanks are on the left. This is a refinery we just finished off. It's the first new complex refinery that's been built in North America in the last 40 years. It takes bitumen and turns it into ultra-low sulfur diesel. It was designed, when we started about 15 years ago, we incorporated carbon capture and storage right from the initial design. So it's the only refinery in the world that was optimized around carbon capture because it's the most recent one built. It's the first of 3 phases that will ultimately be built at this site, and we spent just over $10 billion building phase 1. So my main message is engineers respond to signals. If you give us the right signal, we'll build the right things. Government's in charge of those signals. They're starting to send them out properly now, and we think that that will result in a lot of advances in the world of carbon capture and storage, and I'm really hopeful that this is going to happen quickly. When you send these signals, things start to change, and they change for the good. I'm going to give you a few examples of that over the next slides here. So this is flaring in Nigeria. This shows what's happened with SOx and NOx. It says projections on here was an old slide, but this has actually happened. This is an old slide too. It's flare gas in Alberta, and it ends in 2007. The trend kept continuing. It's down to almost nothing now. What's happened with deep sulfur in diesel fuel and gasoline is truly astounding. It's down to now where you have trouble measuring how much is in there, and it started for very high sulfur contents back in the day. So all of this is a result of regulatory changes that were made and implemented, and they didn't destroy the industry when they did it. They worked with industries so that these changes, the economic cost of them, could be managed. So where are we now in the CCS business? It's just the start. It's like when Brunel built his great ships back in the mid 1800s. There's lots to do and lots of improvements to make. So the history of Northwest in the CO2 business starts down in back in the early, 2002, 2001. We were involved with the Pan-Canadian at the time in implementing a project to bring CO2 from a coal gasification plant down in Beulah up to Weyburn in Saskatchewan, where there was a big oil field that would respond to CO2. It's about a 300-kilometer pipeline that was built, and it's been in operation since that time. This is the coal gasification plant. It was built with a grant from the DOE back in the 70s, I think. It's a truly enormous plant, but we learned about gasification in it. And one of the main things with CO2 is most of the costs that make it expensive are in the costs of cleaning up the stream. So if you start with a pure stream, the rest of the puzzle isn't inordinately expensive. It's less than $50 a ton if you start with a pure stream. This is the refinery I showed you earlier. The main features of it related to carbon capture are it incorporates what we think is the world's largest operational blue hydrogen plant. We make about 150 million a day of hydrogen there, and associated with that, we make about 4,000 tons of CO2. The process is optimized around the capture of that. It starts off being pure from the get-go, and that saves a lot of cost. These maps show something we call the Alberta Carbon Trunk Line. It's a system that's conceived as a sort of a collection utility from all of the industry in central Alberta, and it takes it to oil fields and depleted gas fields in central Alberta, where we can either use the CO2 for EOR or dispose of it for pure sequestration. We spent around $1 billion building this system. It's a 240-kilometer long, and sorry for mixing units, 16-inch diameter pipe. If you go all the way through, it handles about 15 million tons a year. That's the design capacity. But if you're taking CO2 off at intermediate points, it'll handle a lot more than that. These are just some shots of the CO2 equipment. That's a CO2. It's a 10 megawatt compressor. It's just under test in the man shop in Germany before we brought it to the site. That's inside the CO2 building at the refinery. The compressor is on the right-hand side with those sort of blacky pipes coming out of it, and then the outlet you can see with the yellow label on there. We're handling about 4,000 tons a day from phase 1 of the refinery. This is a booster compressor that's immediately adjacent to the refinery site. It compresses the CO2 further, and it also collects CO2 from a nutrient fertilizer plant that is in close proximity, and we get about another 1,000 tons. So out of this system is coming about 5,000 tons a day, and it's at full pipeline pressure. Sorry to use the wrong units again. It's about 2,600 psi, so that's full injection pressure when it leaves this compressor station. That's just a shot of us drilling the injection well for the first CO2 out there. We've now put about 2 million tons of CO2 in this reservoir, and that's in less than a year. This shows the facilities for injection at Clive, which is northeast of Red Deer in central Alberta. So what's next for us? We're starting to work on hydrogen. We think that's the most economic of the low carbon fuel sources. We think it's at least a transition fuel. So we're starting to spend a lot of effort trying to figure out how to be in the hydrogen business. I won't spend a lot of time on this slide, but I think we believe that low carbon hydrogen at the industrial scale is a really difficult thing to do. And most of that's related to the economics, but it's also related to the enabling legislation that allows you to do it. The only place we think it can work in the short term is in industrial facilities where you have the industrial strength safety procedures and regulatory environment to be able to handle them. We still think hydrogen is one of the best transitions to net zero, the most economic transitions, and so that's why we're interested in it. Our plan for using hydrogen involves supplying the hydrogen as fuel to existing power generation plants. Many of the turbines can burn high ratio hydrogen, and we plan to make hydrogen at the site, move the CO2 that's associated with that from the natural gas back to functioning CCS system, and we think that's a lot easier than trying to move hydrogen around. So you make pretty large quantities of CO2. We've sized our standard plant for 60 million standard cubic feet a day. We think that fits well into an industrial scale power plant, like sort of the 200 to 300 megawatt size. The CO2 that we make from that stream is about 1,000 tons a day. And so that's a quantity that we can handle by rail. And most of the power plants that would be the first adopters of this are far from CCS systems. And so rail is really the only practical way to get it back to a place where you can store it safely underground. We think this works today. The thought I'd like to leave you with, it's a lot easier to move CO2 than it is to move hydrogen. If you're making hydrogen from natural gas, you're going to have to move CO2 or you're going to have to move hydrogen. I think it's best to focus on the CO2 for the reasons listed on the slide here. So thanks for listening to me. I hope I haven't overrun my time too bad. If you got a question or you want to talk to me about something, send me an email. Thanks.
Great, thanks, Ian. And you've joined us live now as well. If there are any kind of pressing questions for Ian, Stuart says you showed a rail wagon for CO2 with priced at $40 to $70 a ton. Is that just for the transit costs, or does that include capture as well?
So if you start off right, if you start with pure CO2, you'll be at atmospheric pressure. You have to compress it, and then you have to get it and load it on a rail car and then get it back. And so that is what I think the range of costs is for compressing and transporting and injecting a pure stream.
And then Ben Stewart asks about your hydrogen strategy and what your break-even price points are for green and blue hydrogen.
That's a complicated question. What we're planning on doing is building something we call a small modular hydrogen plant. So it's going to be a plant built in a factory, not a construction project. And we believe that we can significantly reduce the costs of the plant by doing that. And we think we can be competitive in an environment where CO2 is costing around $100 a ton.
So let's, Vic reminded me we should try and do more of our Q&A at the end. And so we'll reserve maybe more of these for later, but maybe without further ado, I'll turn the floor over to Abigail, who will be talking to us about the situation in Mexico.
Hello, everybody. First, I would like to thank the UKCCS Research Center for the invitation to give this short talk. So I will give a short story about CCUS in Mexico. Next slide, please. In 2012, the Mexican Congress approved the General Climate Change Law to reduce the greenhouse gas emission. And to fulfill this target, Mexico is committed to reduce its greenhouse gas emission by 50% below 2000 levels by 2050. And one of the strategies to realize this reduction is to increase the participation of clean power generation in the electricity market. According to the Energy Transition Law published in 2015, The expected goal of clean energy share in the electricity market in 2018 was 25%, in 2019, 30%, and 35% in 2024. This is in the short and intermediate term, and in the long term, it's expected the percentage of clean energy in the electricity market could be 40 in 2030 and 50% in 2050. This year, the objective described in the Energy Transition Law was evaluated. This graph shows the real operation of electricity market. In 2018, the real share of clean energy was 22%, as well as in 2019, against the expected one, 25%. So we were 3 points below the plan. 2020 was an atypical year because of the pandemic, and clean energy reached around 26%. Wind and solar were the renewable energy that increased significantly from 2018 to 2020, and hydroelectric energy reduced its participation. However, in this administration, the plan is to repowering the hydroelectric in order to increase again the participation in the electricity market and to increase the participation of clean energy in the electricity market in Mexico. As a developing country, it's important to consider the increase of the demand of electricity because we are still growing, especially the population. The installed capacity of fossil fuel plant will increase around 12.8 gigawatts from 2020 to 2034, which means that additional 31.6 million tons of CO2 per year approximately would be emitted only for the additional power. So it is very clear that CCUS will be needed even with a significantly high increment of the renewable energy, which is expected to be 77%. From 2025 to 2034, green hydrogen is expected to be part of the electricity sector with 1.31%. So the climate change will need the participation of both developed and developing countries. Probably more CCUS projects are needed in developing countries than even in developed countries because, as I mentioned before, we are still growing. Next slide, please. The interest of CCUS in Mexico started more than 10 years ago. In 2012, the North America Carbon Storage Atlas was published. In 2014, the CCUS technology roadmap was published with a plan until 2024. In 2015, for the first time, government, academia, and institutions joined in the efforts to push forward this technology. And in 2017, the master's degree in CCUS was opened in the biggest Mexico university at UNAM. And in 2018, the CCUS technology roadmap was updated. Next slide, please. So this is an example, just an exercise to show how CCUS could be a source of revenue for the electricity sector. Considering the incorporation of CCUS in the existing installed capacity in Mexico, that is around 26 gigawatts plus the 12.8 gigawatts of future projects, and taking account a carbon incentive of $9.6 per ton of CO2, and giving CO2 economic value for enhanced oil recovery or for converting CO2 in products with high economic value. As we can see in this graph, at higher CO2 selling price of $35 per ton of CO2, CCUS could bring a revenue depending on the percentage of the installed capacity where CCUS could be installed. This could be a mechanism to encourage developing countries to develop CCUS. We don't have enough economic resources, so we need support from the, now we are working with the amount of sources of the utility, but I think that we need more sources to push forward those projects. Next slide, please. So there are some projects in place. As mentioned before, we are limited for the amount of resources. We are working with the resources of utility, but we are aware that a lot more is needed to meet the climate change challenge. We are working with the utility, the Federal Commission of Electricity, and we are a project that are funding for them. That is the engineering design study for carbon capture on natural gas power plant. Especially, we are working with the project that is the power plant that are going to be built from 2020 to 2024. And with these 8 power plants that we show here in this map, that is in blue point, we are going to work with some of them for capture ready and another for retrofitting. The advantage of Mexico is that we have opportunities for enhanced oil recovery. As we can see, we have 3 oil fields that are candidates for carbon capture for enhanced oil recovery: Burgos region, Chicontepec region, and Cinco Presidentes region. As well as we have the opportunity for storage onshore, for CO2 storage onshore, that is shown in this map in green. We are going to work on a pilot plan on green hydrogen and in a study to know the potential and demand of hydrogen. So I cannot give more details because it still is a confidential project. And we are working with some private companies related to the engineering study design for retrofitting natural gas turbine combined cycle power plant. But still, it's confidential. The company, we have a confidential agreement not to mention, still not to give more information about this project. So this is the project, the current project that we have in place. Next slide, please. So we have a future and possible project that maybe it's going to be funded by the utility. For example, we are thinking to work with to identify location for the clusters. This similar to the UK, around Mexico. We have the opportunity, as mentioned before, for enhanced oil recovery, for CO2 storage onshore. And we have some industries that use CO2, some industry that with a high potential to convert the CO2 for a product with to convert to a product with high economic value. So this is what we have. We have a new refinery that we are looking for funding to work with this refinery to prepare them for net zero ready. So this is the project, the possible project that we have in place. As mentioned before, we are just working with some funding from the facility, but we are trying to look for more from the World Bank and for other institutions that to make this project a reality. So thank you so much. This is my short talk.
Great, thank you, Abigail. Maybe we'll go straight to Alissa, and we'll take some questions, all the questions at the end.
So good morning, everyone from New York City side, but I guess it's afternoon in UK. Too bad that I'm not there. Hopefully we'll be done with the pandemic soon and we'll be able to have open discussions in person. Today I was asked to talk a little bit about a short presentation on what's happening in the United States. I think things or what happened in the United States, as you may know, we have a new president, a new government, and things are very different. In fact, one of the biggest change I will say is that the name change in one of the offices within Department of Energy. So within the Department of Energy, there are different offices, and one of the offices was Office of Fossil Energy. And now the name of this office is Office of Fossil Energy and Carbon Management. So as you can see that there's a big emphasis not only for net zero, even negative emission technologies within the United States happening very rapidly. Next. So this is an interactive map for carbon capture projects in the United States. You can take a look at it at the NETL, National Energy Technology Lab website on US Department of Energy. We still have a lot of ongoing, which is a kind of legacy projects, as well as the new projects in the United States. Most of the blue dots you can see here, those are post-combustion capture technologies. Currently, we have about 81. We have about 10, and these are the quite healthy number of projects, but at the same time, I think some of these are quite mature. So we are adding a large number of new projects to the mix at this time. Next. So one of the biggest highlight we can show, and we've been showing last few years, was our Petronova project. Similar to Boundary Dam project, it was a large scale, and we were doing it in near Houston, Texas. And this is the photograph at the bottom, which I took in September 2017 when we had a big mission innovation workshop on CCUS. Next. Unfortunately, this project ended May 1st, 2020. So we are not sure when we're going to revisit. Hopefully with the new government, we'll restart. Because the data from this particular demonstration, I think it will be critical for us to scale up and commercialize our CO2 capture technologies from especially point source. Next. So as you can see in this slide, there are a large amount of, as we saw in the projects we already have, we have large effort in post-combustion as well as pre-combustion capture technologies, which are really critical for us to reach zero emission. Some of the materials they've been working on and testing are advanced solvent, liquid solvent, solid sorbent, membranes, and hybrid systems, and both for post and pre. And because of all the discussion happening last 5 to 7 years, really actively in the United States, we start looking at other areas. It does not mean that we're going to shift the gear. We are still focusing on post and pre-combustion capture, but we are adding new areas. Next. Those new emerging research areas is that how to decarbonize industrial sectors. For example, petroleum refineries, iron and steel, as well as ethanol plants. Those are very different concentration of CO2 and different impurities. So integrating CO2 capture and storage technologies to these industries could be quite different. And big emphasis in this particular US government is on decarbonization of industrial sectors. And other area, go back, please. Other areas we are also looking at is negative emission technologies. And in the past, we thought that we should be really focusing on zero emissions. So there was less emphasis from federal government on direct air capture, for example, or biomass with carbon capture and storage. But with all new emphasis on decarbonization of different sectors beyond power sector, parallel effort with post and pre-combustion capture, now we are also looking at negative emission technologies. Next slide. So what is our projection? This was a very interesting report published last year, June 2020 by McKinsey. It was their projection on potential in 2030, which is not even 10 years out. So if you look at this picture on the left, there's a storage potential, light gray. I hope that this number is underestimated and we get there with a much bigger volume. At the same time, if you look at these darker bubbles, they're saying that while we are really hoping to do carbon capture and storage to really draw down CO2 and lower the CO2 emission in atmosphere, we can also utilize CO2 just because there's a market for it. So you see that fuel is a big bubble, and there's a construction and biochar, enhanced oil recovery, as well as other specialty chemicals. Next. This is important, and I think people relate to very well. This is a beautiful picture of New York City when it's sunny and nice weather. As you can see, click next, that there are so many materials, and this entire city itself has a lot of carbon in it. So if we say, can we decarbonize? We talk about decarbonization of power sector. That makes sense because we can do that with renewable energy. But at the same time, if you're looking at that entire society and material sector, we cannot decarbonize because carbon is a critical element to build all these. So next. So we should think about not decarbonizing, defossilization of chemicals and materials. And that becomes new questions on how to manage carbon throughout our engineered system and natural systems. Next. So overall, looking at, can we develop the new circular carbon economy using the carbon throughout our systems? Definitely, if you look at the blue circle, which is our society, we can make chemicals and materials and fuels and you use them, and some will end up in waste streams, some will end up in ambient air. Next. So if we can kind of put it back into circular mode by using only renewable energy and hydrogen with the low carbon intensity, and some of the previous speakers already talked about a little bit. Next. This involves in carbon capture, very innovative, and from wide range of sources, including directly from air, and then convert with maybe chemically and biologically or even hybrid mode. Next. And all these things to think about how to go from tech to market because the commodity chemical market is huge compared to specialty chemicals. And we are redeveloping entire new circular carbon economy. Next. And all these decisions are made based on economics and policy as well. Next. So looking at the ambient air as a source for the entire circular carbon economy, next. There are different technologies you can do. So you can either go through a biological medium or you can chemically capture CO2 directly from the environment. So if you look at the letters at the bottom of the figure itself, where can we get non-fossil carbon to create the whole new economy? It could be from air or ocean, or if you're going through biological, it could be terrestrial or marine biomass. So there's a great, interesting report published in 2019. You can take a look from National Academies. Click next. So let's look at the direct air capture, which I was asked to talk about a little bit. Next. This technology is a little different. This is the photo is showing Climeworks in Switzerland, and now they're deploying this technology in many different locations right now. Compared to point source capture like power plants, it's quite different because concentration of air is very low. Next. It's at 400 ppm or slightly higher depending on where you're located. Compared to 12 to 15 volume per cent fired power plant, now you have to think about what is the binding energy we need to use. Because of that, capturing 90–95% plus of a CO2 from air is not economical. So next, we are looking at maybe 60+% of CO2 capture is good enough. So the targets are very different, rates are very different, and challenges are very different. Next. So some of the challenges specific to direct air capture is you need very low pressure drop, and you need to have very good stability with high oxygen concentration in air. And you have environmental conditions fluctuating, humidity and temperature fluctuating wide range. And you need to deal with other pollutants and impurities, including the dust and all that so on. Next. So let's look at what we've been funding and supporting in the United States from the government. Of course, we also have a large amount of industrial grant supporting this R&D. But if you look at the mid picture, click next, you see where direct air capture is. Still, majority of our research on R&D project is on coal. But we are also starting to do a lot more research on natural gas and a little bit of industrial sectors, but direct air capture really increased the amount of activity quite a bit last year and two. And if you look at on the left-hand side, what type of materials we're looking at? There's a liquid solvent and a solid sorbent. Those are major. We also work quite a bit in membranes. If you look at on the right-hand side figure, what scale? We are still heavily focused on laboratory and bench scale research, but we also have a number of larger scale demonstration as well. And hopefully that these bench scale will be moved forward to the higher TRL sooner than later. So let me focus on direct air capture. What are the newest ideas in the United States we are really considering? Next. So in terms of direct air capture materials, we are focusing on mostly solid sorbents, which is similar to what Climeworks is doing. So that the keywords you can look at is hybrid, MOS, dual functional, and tunable materials. There are only few options we are considering for liquid solvent. Because of that, direct air capture is much easier to deal with solid sorbent. There are different degradation mechanisms that we are studying. Next. So we are also looking at not only the functional materials capturing CO2, but how to load them up and then expose them to the directly in air. So multifunctional structural sorbent, maybe they can protect them from water by selectively rejecting waters. There are a lot of fiber designs or capsule designs, as well as a membrane with absorbents on the surface. 3D printing is also used, and also redox active textile. All these are the new ideas being considered for direct air capture. Next. Another big area is for direct air capture. Since direct air capture is kind of decoupled or can be decoupled from power generation, now they're looking at, can we use renewable energy to do the energy transfer to regenerate these solvent materials? So looking at the electron swing, and which we consider to be energy intensive because we thought about linking with the traditional power plant now coming back. So there's a new way of thinking of either electricity, microwave, many other ways to efficiently transfer non-thermal energy to regenerate solvents. Next. Applications are wide. We're looking at the even building airs. Next. We're also looking at the integrated systems combining water and CO2 capture or combine CO2 capture with CO2 conversion. Next. And the last area, which I'm not going to touch upon much, is that not only direct air capture, we are also looking at direct ocean capture. Next. So this is one of the examples. In fact, in my research group working with Michelle Kidder at Oak Ridge National Lab and Yongju at Cornell, we are working on. So looking at novel materials can capture CO2, which we actually developed for point source capture. Now we are delivering it by putting into fiber systems so that we can really minimize the pressure drop, and that fiber system can selectively reject water so we can minimize parasitic energy consumption. Next. So which direction are we going? This is an all big picture in the United States. We are really focusing on carbon management at multifaceted way. And if you want to really create the new carbon economy, you need hydrogen as well. So the first one we call energy earth shots was on hydrogen economy. So we are targeting $1 per kilogram of hydrogen in 1 decade. This was announced in June 2021. Next slide. The most recently, we also announced from Department of Energy is looking at long duration storage shot. So should we store hydrogen or hydrocarbon? There are many options. I think it's interesting time, important time in the United States moving towards the carbon management integrated with new carbon economy as well as a hydrogen economy. I'll be happy to answer any questions. Thank you.
Great, thank you, Alissa. And then our final speaker is Howard Herzog, and then we'll take questions at the end. Howard, the floor is yours.
Okay, thank you, David. I'll let my slide come up. Okay, it's a pleasure to talk to everyone today. Give you a perspective from the United States. Next slide, please. So what's driving CCS in the US today? The major thing is the 45Q tax credits. It's a federal program where you can get $50 per ton of CO2 stored in geologic formations, or if it's going for enhanced oil recovery projects, you get up to $35 per ton stored. This means mostly the people are going to be able to take care of this are people that have pretty pure CO2 to start with because it won't cover the cost for capture. There are state programs that have different aspects to help CCS. The most significant is California, the low carbon fuel standard, which is about a market price of $200 per ton of CO2. I'm not going to go into the details of that. They have a lot of fine print on it. You have to get this low carbon fuel to the market that CCS has helped produce, but it has induced quite a few projects that are being explored at this time to try to take advantage of that market price. Other things that are happening, there's stockholder pressure on large companies. Earlier this year, a lot of headlines about Exxon and 3 new people on their board. And so these companies are really, what should I say, they have their attention, and a lot of them are banking on carbon capture and storage as part of their future. We see cash coming in from technology companies. These are the Googles and the Microsofts of the world, that they all want to be carbon neutral, and they all want to go back and be carbon neutral. So they're infusing money, especially into what I would say carbon removal projects, so they can create some negative emissions for themselves. And they're willing to pay significant cash for it. Then there's also this, finally, the growing realization that we no longer afford to ignore climate change. And I think that's been brought home this past few months with the hurricanes and the fires in the US. Next slide, please. So I'm going to talk a little about policy and what's going on. And there's 3 key legislative bills. The Omnibus bill was passed last December, and that had a provision for CCS in there by extending the 45Q tax credits by 2 years. The 2 big bills that are actually front and center right now is the bipartisan infrastructure bill. This was passed by the Senate, and the House has promised to vote in September. It has $12 billion for carbon capture and storage in it. I'll talk about more details in a moment. And the second bill is reconciliation. So the bipartisan infrastructure bill is about $1 trillion. The reconciliation is going to be $3.5 trillion. Climate change is going to be a key set of components in there. How big is yet to be known, and what the CCS provisions, that's still evolving. In fact, basically Congress has taken up writing this reconciliation bill as they go back to Washington today to do that. Next slide. In the bipartisan infrastructure bill, they have 6 basic areas for CCS. They have money for transportation infrastructure, mostly in the form of low interest loans. They have development of CO2 storage sites, increased funding for both the Environmental Protection Agency and for individual states to permit CCS projects. This is through the underground injection control program and class 6 wells. It instructs Department of Interior to promulgate regulations for offshore storage. There's a lot of legal matters to clear the way for offshore storage, and this bill has moving forward to clear those barriers. It's going to fund 4 regional direct air capture hubs. Each of these have to be more than 1 million tons of CO2 per year. And it's not just for the capture itself, but for the whole thing, the whole infrastructure there, including looking at utilization of the CO2. And finally, money also for funding large-scale pilot and demonstration projects of CCS. Next slide. And reconciliation, this is, as I say, a work in progress. One key focus of the CCS community here is to expand the 45Q tax credits. I've heard numbers trying to get that lifted to about $85 per ton of CO2, which I think would really be a major game changer in being able to fund projects. There's a lot of uncertainties. Will this bill even pass? How big will the overall bill be? And what will the CCS share be? A lot of politics in this bill. The progressives, which are probably the biggest force behind this reconciliation bill, are fairly skeptical of CCS. If they had their druthers, they'd keep anything for CCS at a minimum. Joe Manchin, however, is really the deciding vote. He's the 50th vote in the Senate, and he is very supportive of CCS, has been. He's from West Virginia, a coal state, and I've seen him in many CCS meetings in the past. So my prediction is if reconciliation does pass, CCS, I think, will get a a pretty good share of, let's call it the $3.5 trillion worth of pork. Next slide. What are some projects? There's been a lot of projects that have been thrown out there. It's very easy to throw out a project. You just put out a press release, but I'll just highlight two here that have my attention. One is called this Houston CCS Innovation Zone. This is basically what one would call a hub in Houston. It's ExxonMobil is spearheading this proposal, and it would eventually, if it goes through, be up to 100 million tons of CO2 per year. They're counting on a lot of policy that's sort of included in the bipartisan infrastructure bill, as well as what they hope to be included in the reconciliation bill. There's also a project, a pipeline to connect upper Midwest ethanol plants to storage sites in North Dakota, states like Iowa, Minnesota, North and South Dakota, to ship where there's a lot of ethanol plants to ship it there. This will be about 5 megatons per year from a company called Summit Carbon Solutions. And at least to the best of my knowledge, I think they can make this project work under the existing 45Q credits that are out there. Next slide, please. I get a lot of phone calls from small companies that are evolving. There's a lot of activity that sort of doesn't make the press releases. And this is one that just came up a couple of weeks ago. I am actually involved in this company, CarbonVert. I've signed on as an advisor to them. And here, we just announced that CarbonVert and Talos Energy were winning bidders for some off-site storage locations off the coast of Texas. So this is one example of, I think, many things that go on that don't get a lot of press, but there's a lot of people working at the level of trying things, actually get things working out there. Next slide. So every silver lining has a little touch of gray, so it's not all positive news. This is actually something that had happened a year ago, February, but all of a sudden it's just getting some press thanks to our friends at Huffington Post. But it's very interesting, and the words used here is basically a CO2 pipeline rupture. They call it exploding, and it engulfed the whole city in Mississippi. This noxious green fog left residents confused, convulsing, foaming at the mouth, and even unconscious. So, as you can see, there is challenges to CCS, even though I've never heard of, my understanding is CO2 is an invisible gas, and it doesn't cause necessarily foaming at the mouth. So anyways, next slide. So I'm going to summarize and say, in the US, CCS is moving forward after basically a decade of treading water. The current policy has given CCS a big boost, and I think with the reconciliation bill, we'll see even a bigger boost. But it's really insufficient to drive long-term, large-scale deployment. So while you might have money for pilot projects to develop storage sites, that's good. But long-term, you need some sort of incentive, some sort of markets being made. 45Q could make some of those. But what we see coming on is, I think in the US, an economy-wide carbon pricing is highly unlikely, at least in the near term, meaning in the next 4 or 5 years. And we'll need to rely on subsidies and mandates. 45Q is the main subsidy for CCUS, but mandates can become important too, especially when you're making mandates, say, of portfolio standards. Is it going to be, say, a renewable portfolio standard or a clean energy portfolio standard? Where clean energy portfolio standard could also include CCS. So things like that as we move on will be very important to how we can get CCS scaled up from the megaton level it is today to the gigaton level we need. And finally, as I showed by that thing about the CO2 pipeline rupture. As CO2 grows, a key question is going to be public acceptance, both at the project levels and at the policy levels in Washington and the different state capitals around the country. So I'll leave it at that, and we can go to questions.
Great. Thank you, Howard. Thank you, everyone, for some excellent presentations. We've had a number of questions about a couple of the specific presentations, and maybe while we're waiting for others to chime in, we can maybe start on those. And I know I have a few questions of my own, but maybe I think there was one still from Ian's presentation from John, I think. Is that right? Yeah. So back in Ian, how much of for Ian, how much of the carbon in the fuel is captured in the hydrogen manufacture plant?
With the process we've chosen, we're getting higher than 90%.
Great. And then from Ben Stewart, how much do you have to modify your QRA processes for CO2 operations?
I don't know what a QRA process is.
Ben?
I'm old, eh? Can you see me?
You're quite dark and ominous looking. It's very mood lighting. I like it. I like it.
Early. Sorry.
Ben, can you explain what a QRA process is for us? Right. HAZOP reliability.
HAZOP's in a refinery, these are minor things. We're compressing CO2. CO2 explosions, contrary to the press, are hard to have because CO2 doesn't burn. So I don't know what an explosion would look like. But no, we don't have to modify things much. We designed the process from the get-go to manage CO2, and it doesn't drive the cost much, that part of the process.
Great. I'm going to have to look into Howard's CO2 pipeline, which I just saw was actually, the pipeline was from February 2020. The story only came out like a year later. For Alissa, we also have a few questions, again, from John. You talked about DAX, but we didn't say very much about bioenergy with CCS. Is it being encouraged? And maybe Howard can also chime in on any BECS proposals.
Sure. So there's a lot of movement on direct air capture and storage. I think that is definitely happening. The question is about bioenergy with carbon capture and storage. I think things have changed in the United States in a sense that if you're just looking at the biomass, like burning wood chips, things like that, it's not as much anymore. But because of the CO2 from ethanol plants are quite pure, you don't really need to do much to capture that CO2, if you call it capture. And then using that to utilize or store somewhere, that activity is definitely happening. And in fact, most of the CO2 conversion researchers in the United States say, oh, we're going to get CO2 from ethanol plants because that's the cheapest and easiest one to get today. So I think there are activities, whether it's going to make a big dent in our net carbon emission, I'm not sure, but that's one area. Another area, people have been looking on algae for a long time, and then how to use algae better. The challenge was dewatering and energy-intensive dewatering, but now looking into how to do that better, as well as going into marine biomass. So that's kind of blue carbon area we can tie into. So that area is new and actively working on because it doesn't compete with the land use change. So maybe, but it's not a big bubble in my view at this point. What do you think, Howard?
So we wrote fairly, I think it published earlier this year on bioenergy and CCS, and this more along the tracks with the electricity production. And our analysis says I think this is one of the best negative emissions pathways forward. Unfortunately, it hasn't caught the imagination like the direct air capture. I also wrote on direct air capture about how expensive it is and how expensive it's going to continue to be. So I'm not quite sure why there isn't more interest in the bio. There is a section of the environmental community, the US as well as around the world, that's very negative against biomass, period. Don't give us any details. We just don't like biomass. And you're not going to change our mind. So we'll see how that goes. But yeah, there's not, at this point, I don't see a lot of activity. I know there is a, in California, I think with Chevron and Clean Energy Systems are talking about doing a CCS and a biomass plant out there. And there may be some others, but it's sort of not captured the attention as the direct air capture things have. I think in the long run, fundamentals will win out and things will change, but it will take time.
Well, I'll just pop in for a sec. One of the projects we're looking at is co-locating our small modular hydrogen plant at a site where we can gasify wood fiber from a sustainable forest. And we think the two of those overlap pretty good together. The problem is you can't build a very big biomass plant. Like we're looking at 1,000 tons per day, and that's a pretty big sustainable forest. So there's limits on what you can, how much you can do, but we think that there's a good application there. And if we can do it at a site like that, then we get sort of carbon negative from the bio stuff, and that adds up pretty well with the rest of the natural gas stuff we're doing.
Abigail, do you want to weigh in? Is there any interest in Mexico in either kind of bioenergy or direct air capture, or is that still too early for that?
I think that it's too early. We are working more on biomass, but not with carbon capture. But I think that net zero negative CO2 emission, I think that it's early for Mexico.
And again, in terms of different applications, Ben has another question about, well, for Alissa, but more generally, have you investigated the economic and ramp-up potential of standalone integrated CCUS industrial plants, as well as large-scale projects?
So that's an interesting question, because I was wondering why last 5 years we start focusing so much on direct air capture. Although we know that this is very challenging technology, as Howard said, I think one of the reasons is that because they somehow developed this entire direct air capture systems as a modular design. So that a lot of VCs or even smaller companies can get in and then make a smaller unit and demonstrate. And that really appealed to so many different people. And the fact that we don't need pipeline, you can build this near the injection site. For example, Climeworks is working with Carfix in Iceland. So there are some positives to kind of deploy in the field with the smaller scale. I think that made it a lot faster or more interest in industry, maybe. So I think it would be, they argued that instead of scale up, it would be scale out. So a lot of copy paste. So it would be faster learning curve. I think we need to do both, right? There's an economics of scale at the same time, a learning curve of continue to improving the system. So I think DAC development has been a little different than point source capture, when point source capture was a lot of capital intense, large scale. So how do we estimate the economics and ramp up scale up potential? It has to be kind of dealt differently. Should we always have a DAC as a smaller system? I'm not sure. Those are the discussions we should have now, but because of the uniqueness of how DAC was introduced, I think that's why there was a faster commercialization in their mind.
Well, and people who do this don't start with a heat and mass balance. So if you look at the direct capture, the number I've seen is like 5 megawatts per ton of energy to capture 400 parts per million in CO2. That's a CO4. If you think of these things as mines, I'm going to go to the mine with the richest ore in first. I'm going to go to, if I could find 100% purity, I'd go to that. And then I'd economically progress down that continuum to the worst mines. And so direct air capture just happens to be the worst mine. It's going to be hugely energy intensive to capture that. And then people don't spend any time thinking about the water use. You know, the water use.
Don't get me wrong, Ian. I'm not saying that we should stop point source capture and then do negative emission or direct air capture. I think that's where we went wrong. Like, I think, as I mentioned, point source capture has to continue. We have to decarbonize. There's no question about it. But then should we stop doing direct air capture research or not? That's a different question. If all the research funding is going towards the direct air capture, I'll be against it. But when we are looking at the really fundamental research, thinking that any technology takes at least 2 decades to be commercialized. Having fundamental research on direct air capture is okay for me, and no point stopping it. But while emphasizing the point source capture urgency, and I think as long as we're open-minded in this and agree on what is a priority, we'll be okay. But I think it's not productive if we say one versus the other, because similar to BECCS, we need to be really open-minded. This is such a big scale. We need to do it all. And some of the options will be very location specific. And I think that's the key message I want to have.
Okay, and the message I'd like to leave is you can't do everything. You have to do the things that you think you can do, and we have to start doing things quickly, not 20 years from now. And so what we should do is start all of these discussions with a heat and mass balance and say how much energy is going in, how much water is going in, and how much CO2 is coming out. And that'll tell us about something about the likelihood of making it work. And this topic seems to defy all discussion, normal engineering discussions on numbers. We need to look at numbers. How many megawatts per ton does it got you to get it? If it's off the scale, then don't spend a lot of resources on it, because you can't change the laws of physics. They're not guidelines.
Let me say a couple of things. One, I wrote a chapter for a book that's coming out in February from the from the UK, the Royal Chemical Society, and it's on negative emissions, and my chapter's on direct air capture. And I talk about the laws of physics in there, and I'm happy to send an advanced copy to anybody on the phone call here or on the webinar here, and just send me an email and I'll send you the copy out. It's hjherzog@mit.edu. The second thing is, I think one thing that's given direct air capture a boost is what I had in my slides, the money from these technology companies. And they just want, we want to erase our debt. They have a lot of money. And if you go to the Climeworks website, which is the only place you can buy negative emissions now from direct air capture, the selling price is $1,100 per ton of CO2. Now, who's crazy enough to pay that? There are people that are doing it, but they have people, they have a lot of money. But that doesn't decarbonize the world's energy systems, because most people can't afford $1,100 per ton of CO2 as some of these technology companies can. To them, it's just a marketing thing, saying we've raised all our carbon debt.
So I would like to give my final comments, that I think that it's completely different than what you are discussing. I think that the carbon incentive is very important to take seriously the carbon capture, for example, in Mexico, because of the incentive in California that is put forward private companies, the Mexican government to think about hydrogen and carbon capture. So I think that this is going to move, especially in developing countries.
That's a very good point. Maybe, somewhat relatedly, maybe to this more general discussion, Ben asked Alissa, but again, it's a more general point about, have you developed a net zero calculator to evaluate the impact of the environment, social, and economic trade-offs when comparing technology options? Because this is exactly the sorts of issues that I guess we're talking about here, just how big a difference there are between the different approaches.
I totally agree. That is one of the critical things we need to have. But what is the best calculator? That's debatable. I think it's really wide range of things we need to consider, as he listed here. But one of the things is, I think the best life cycle analysis or TEA analysis is only as good as the data availability. So I think on our side, who are doing tech development, we need to share more data. We should produce more data, and then so that we can feed that into the calculator. So not only the framework of the calculator has to be good, we need to have a robust set of the data to test all these different options, because not only we need to say, okay, we're going to develop this CO2 capture technology, but storage side and how to put the pipeline, like how we talked about, there are many aspects of like whether we can even get public acceptance or permits, even running all these pipelines. I think it's really limiting if we try to compare everything to apple or fitting it into apple so that we can compare, but we should understand the overall what it does for the entire system. Then we can truly evaluate different technologies. I think we are learning a lot more because each DOE meetings, there's a national lab driven direct air capture, or not only direct air capture, CCUS life cycle analysis and TEA frameworks. I think we are getting there, but this will be taking a little longer time to have a robust one, in my opinion. But there are a number of good articles, including Howard's group, looking at this and then publishing. So hopefully we'll get there sooner than later.
I guess maybe one final question I might obviously ask is to do with the sort of political support for these projects. I mean, in Alberta, you've lived through some governments of quite different colors and flavors, and you know, in the U.S. over the course of just the last few years, we've seen this kind of oscillation back and forth, as Alissa referenced, the rebranding of the you know, DOE fossil energy plus carbon management now. How do you, but by the same token, these projects are, you know, very, you know, much longer than an individual administration. So how do we make these projects more robust to this type of kind of political ups and downs?
I think the thing that we're starting to see now is it used to be government originated projects. And when we started with the trunk line, you know, that was 15 years ago now. And the government of the day thought that carbon was going to be important and they had to do, you know, they had to make some statement, and so they did it. But now the capital markets are starting to look at, you know, your ESG performance, and what essentially that goes, the environmental part of that is all, what am I doing to mitigate? And your cost of capital for your company is in part determined by your ESG performance. And there's a lot of scrutiny on it now. And there's talk of things like rating agencies for carbon intensity. So just like there's a bond rating agency, there'd be a carbon rating agency. That goes to your share price for your whole enterprise. So it's going to be a direct connect. And I think they'll start driving what the governments do now. They'll start saying, we have to have this. We can't operate in a world without it. And you can see sort of the, you know, cracks in the thing. People used to resist it and say, look, too expensive, we'll do it later. Now they're all rushing to try and make some announcements. Most of the announcements still are fluff and not real activity. But that's going to have to turn, rubber's going to have to meet the road, and it's going to have to do it at scale pretty soon. And I think it's more than the government now. It's the sort of big industrial players that saying, we got to do something.
Abigail, in the Mexican context, do you see this as, I mean, you mentioned private sector interest a lot. Is that primarily what's driving the?
As I mentioned in the presentation, the private sector was interested, especially the private sector close to the cross-border in California, because of the incentive that is given in California. So without incentive, I think that it's not going to be too much interest in carbon capture. But as what moved some private in the cross-border in Mexico to start working on carbon capture because of the incentive in California.
That's really interesting. And then maybe the U.S. can maybe Alissa and Howard can give their kind of final views on how do we make these projects kind of viable over the intermediate term, not just the short term?
Maybe I can have quick comments and Howard can end. So in my opinion, a lot of fundings are still individual PI, smaller grants. And I think we can look only, like when we talked about the good TA or the net zero or carbon calculator, you really need to look at the overall process and process integration. There are not that many good projects like that. And still we're giving funding out to novel materials, novel contactor, or regeneration, kind of piecemeal. And I think they're trying to pull all these projects together and then talk to each other, but that's lacking still. I think if you really want to get there fast, we need to have more researchers talking to each other, not only among ourselves, but also industrial partners who can commercialize these technologies. And I think that that can be promoted and facilitated by government. And hopefully we'll get there sooner. It may not be one big hub project, it may or may not, because we don't want to put all the eggs in one basket either. But at the same time, kind of making sure that everybody's talking to each other and sharing data as quickly as possible, maybe we can get there faster.
Yeah. Howard, I guess the last word to you.
Yeah, I was going to say, you're the political scientist, not me. You're probably better to answer it, but I think things, if you can it's hard to get things in legislation, but if things are in legislation, it usually has longer shelf lives than a lot of stuff with, say, done via executive order, which is what we've been living with the United States for quite a while now. A lot of the climate stuff that came off of the Obama administration was executive orders that Trump reversed, and now Biden's trying to reverse a lot of stuff that Trump did with these executive orders, and that's not a way to run the government. But in the partisan atmosphere we have here, it's hard to get good bipartisan legislation. That's why this bipartisan infrastructure bill if it finally does pass, what I think it will, is such a big deal. Having a bipartisan bill of this nature, it's hard. Now, reconciliation, they'll pass a lot of bills. If Republicans get back in, they can undo it via reconciliation, but it's a lot harder than, say, just a simple executive order. So I think that's one part of it. I also think that, CCS in the US, as we hit about 2008, 2009, sort of hit a peak and then really fell down. And that's because the whole push toward climate sort of fell away and everything. I think because of what nature is giving us a feedback about climate change, I think there's no going back at this point. The question is how fast or how slow we move forward. But I just think that pulling back is going to be very hard for lots of reasons. Climate denial is over. That doesn't mean people aren't throwing monkey wrenches and trying to get to the solution, but so I think that will be helpful.
I think it seems like, at least in the US, CCS is one of the few areas where there is bipartisan, I don't know, consensus, but at least more agreement than on many other areas, perhaps. I wanted to thank our panel for a great discussion. It's a great way of ending our day here. So thank you all. It was a great fun.